Hello and welcome back. You might recall we are partway through this verilog1 module, which in turn consists of 4 units. The first unit is just an introduction to HDL-based design. This second unit is meant to be a complete example, designed from the ground up, a simple counter. And then in later units we'll go through verification and synthesis. The idea again is to give you a complete view of the entire design, verification and synthesis process from start to beginning. Furthermore, I'm using a counter example here, and a counter is a very common element in design, particularly in the control path. So, this submodule is the complete counter example. I'm going to emphasize 3 different things within this particular unit of the class: design before coding, the count.v example, and in the latest submodule, how Verilog works internally. My objective is to really drill into you the mantra, always design before coding, and that's where we're going to start. In addition, I want to have you understand how Verilog works internally and how we can actually simulate the intrinsic parallelism of hardware on a serial computer, which is not obvious at first when you think about it. Again, the point of this entire module is to give you the big picture altogether before we go into the details. And in particular, to start emphasizing to you how writing HDL, or more precisely, designing hardware, then capturing it in HDL is very different than normal code, and how the HDL simulators work internally. Here are the references. This is the first time I've referred to this top reference, which is a web-based reference. Sutherland produces a very nice set of quite concise reference guides. They give an explanation of the features in the language, feature by feature, and then give nice examples of those. And I find when I'm writing code, or at least when I was learning to write code, that this was quite useful for a very succinct reference guide to help me write, particularly because the example is within it. This module is related to a homework which requires some design, and there's a tutorial associated with it. In addition, the reference books have features in them that will help you understand this material if you need it. This is the outline of this entire unit, and what we're going to do in this first submodule is emphasize design before coding, before getting into the counter and showing different ways of coding it. Okay, so this is getting into the second mantra for this course. Of course, the first one was one clock, one edge, flip-flops only, at least within one module. This second mantra is the most important one. Always design before coding. This using Verilog to design hardware is not primarily a coding exercise. You work out your design intent at the register transfer level, then translate that into code. If you do that, you'll end up with a lot better results than trying to just sit down and start typing away. Why do I emphasize this? A lot of people think, well, I'm going to have this synthesis tool. Won't it work out a lot of stuff for me? It doesn't. It won't work out for you what needs to be in registers, and it won't properly construct the behavior of the combinational logic. You have to do that. It does help you with a lot and improves your productivity dramatically over working at the transistor level, but it does not relieve you the task of logic design. Most specifically, what synthesis does do is do the logic optimization for you, get the timing right for you, if that is possible, given what you presented to the synthesis tool, and do some of the detailed logic design in that you can quite often capture behavioral description of how the combinational logic should behave, and you don't have to worry about the details of the gates within it. However, later we'll actually show that adding some of that detail can actually lead to a much more efficient design. And you might recall the discussion at the end of the timing notes showing some of those differences, at least in the structure. If you don't follow this mantra of design before coding, then what's going to happen is you're quite likely to end up with a very poor design. If it works, you'll have a very slow clock, long critical path. It could be very large. And also it could be such it doesn't work, that it's not a proper target for a synthesis tool. And for example, the synthesis tool produces these HDL lint errors, which are flags of RTL that is not actually synthesizable. I'll give you an example that I saw a few years ago. A student came to me complaining about how slow and big his design was. I looked at the code, and he had there a for loop. For I is equal to 1 to 1024, A is equal to A plus BI times CI. It was a dot product type of thing. And this was one for loop within a procedural block. Fine as code, but as hardware, what he had just specified is that there'd be 1024 multiplier accumulates strung in series between a pair of registers. You can imagine how slow the logic is if you have to go through over 1,000 multipliers in one clock cycle. And you can imagine how big the design is, and also how inefficient it is, since while that data is propagating through that chain of multipliers, most of the multipliers are idle for most of the time. He needed to design it first with one multiplier and a counter to iterate through the 1024 cycles before writing the code. Now I'm going to get into temptation. I could be like a preacher here and say, avoid temptation, because I'm going to describe to you some of the temptations you will have within this class. The first temptation is the one that's succumbed to most commonly, and that is, since Verilog looks a lot like C, it has strong roots in C, it is very tempting to capture an algorithmic intent in C, turn it into Verilog with a few always at statements, much for an always at pos edge clock, and sort of hope for the best. This rarely works. An example is the one I just gave, building 1024 multipliers. Typically, you end up with synthesis problems. Sometimes you end up with very vague clock level timing. And you often end up with too many registers because you'll forget that everything assigned after an always at pos edge clock statement becomes a register, whether you intended it to or not. So you better tend it to do so, and you do that by sketching out the design, particularly the registers, with some understanding of what happens between them before writing code. The next temptation is to think that automatic synthesis is this magic tool that can turn bad design into a good design, and it can't. All it is a timing-aware Carnot map optimizer. That's all it is. It doesn't fix things for you. And I've had students come to me and say, why can't the tool fix this for me and give me a good result? It doesn't have artificial intelligence built into it. It's just a timing-aware Carnot map optimizer. And even then, it's actually just approximate. So don't write code and just kind of hope it'll work out. You've got to go through the discipline of doing a design, translating it into RTL, and then presenting it to the tools. Third temptation is a little different, and that is to start trying to write elegant code, possibly with coding structures I haven't actually taught. And there are some that are synthesizable that do work. Particularly for neophyte designers, I urge you to avoid this. That is to go through the discipline of translating the design into code in the most straightforward way possible, rather than do something sophisticated. Experts can consider doing something else, but certainly neophytes should not do this. And furthermore, quite often, the least elegant code gives a better design. Quite often, putting in human level knowledge about the structure of the design, making the code bulkier in process as a result, that actually leads to a better design than one that's just a few lines long. I'll give examples of this later, but again, one example we saw in the timing notes. The examples in there that ran more efficiently at the end of that, where I did the multi-stage comparator, those examples that ran more efficiently actually have more code in them. So let's talk about the steps in design before starting on this counter. The first step in design is to work out the hardware algorithm and the overall strategy. This can actually be quite time consuming, particularly as we get to larger designs, and we'll see examples of this in later modules in this class. In terms of detailed design, the next most important step is to identify and name all the registers. Because doing this really determines the system timing, and since you have to name all the registers anyway, because you have to assign them in an always at pos edge clock block, then this is the time to do that. This is where care must be taken. It's very easy to add in too many registers, which will bloat your design and make it slow. However, you do need the registers that you need, and possibly a few more in order to improve the performance, for example, using micropipelining. How do you decide if something needs to be in a register? Does it need to be preserved between clock cycles? You can think of everything that's not in a register in the code as being lost between clock cycles and being reconstructed from what's in the registers. Thus, the registers have to retain at least enabling data between clock cycles, if not the data you need itself. You then identify the behavior of each cloud of combinational logic. And this is where synthesis is your friend, because you can do this at a fairly high level. And in fact, I carry a lot of the detail here in my mind after determining the registers. At this point, it actually is useful to do a brief simulation of in your head of the design. And I do actually urge you to do that, though I won't be illustrating that in the next few notes because it's a little tedious to do. But once you're confident that your paper design has a reasonable chance of being close, then what you do is translate the paper design to RTL. Note, this is not really a coding exercise like in your C or C++ classes, where you often just sat at the screen and start designing and writing the code at the same time. Here you cannot do that. Design is a separate step leading to a paper design. You then take this and verify it using the simulator, and quite often here you'll have to refer back to your intended timing diagrams to understand the bugs in the simulation. And then finally you synthesize the design and thus get logic at the gate level. So let's start on our example, which we'll carry through for the next two submodules and the units within, and the units going on beyond that. And that is the countdown timer. This is very simple. I have a 4-bit counter. I have an input in, which loads the count into the counter when latch is high. Notice latch is priority. When dec is high for decrement, I want to continue counting down, losing a value 1 per clock cycle. I want to stop at 0, and I want the 0 flag to go high when I reach 0. Again, a counter is a very common element in design. Often we have to count bytes going past, cycles, all sorts of things we want to count. It's a very common element, particularly in the controller in the design. So again, this is what not to do. The first example at the top there is a classic example of writing C, slapping an always at pos edge clock at the front of it, and hoping for the best. And in this case, you get a pretty bad result. When all is said and done, what do you think this actually builds? I must admit, I've never actually run it through the tool, but let's see what happens. Remember, behavior implies function. So pos edge clock comes along. We then execute that for loop from value down equal in down to 0. When it hits 0, the 0 flag will be 1. 0 is the only thing assigned explicitly in this for loop. The value is assigned implicitly. So we're most probably going to get a flip-flop whose D input is tied to 1. And on the pos edge clock, Q becomes equal to 1 through that flip-flop. Again, I haven't verified this through running through this through synthesis, but you're not going to get what you're hoping, where it takes in number of clock cycles to go down to 0. Right, this is going to all happen in one clock cycle. The second attempt here on this page is more sophisticated and is actually most probably actually close to something that would actually work. And that is to put this at pos edge clock trigger in the middle of the for loop, so that every cycle of the for loop is delayed by one clock cycle, and that's more likely to build what we want. This is an example, however, of elegant code, quote unquote, which is not better code. It doesn't produce a better design, but it certainly makes it harder to understand and much harder to follow the design process that I'm strongly encouraging in this class. So let's turn to the actual design. Working out a strategy for such a simple example is overkill. But let's briefly describe what it is. We're going to have a register, we load into it, decrement it while dec is high, monitor the register value to determine when the output is 0. But anything beyond a trivial example, you do have to think through your strategy in your design. We'll talk about that later in the complexity module. So the next and very important step, because if you get this right, you're most of the way there. So the next and critical step is to identify and name all the registers, that is, arrays of flip-flops. What needs to be registered? Anything that needs to be preserved between clock cycles. In this design, the only thing that needs to be preserved between clock cycles is the current count, which I'm going to call value. And it's a 4-bit register producing the signal value. The next step is to identify the behavior of each cloud of logic. And here I can be a little bit loose. So, a very useful way quite often to approach this is to say, well, the register has multiple alternative different sources of data. So let's put a mux in front of it, list those alternatives, then think about the control lines for those alternatives. So what are the alternatives? The alternative next values of value. Well, there's in, which is what we want to load it originally. There's value minus 1, if we're doing an actual decrement. And I often leave this wire out in my examples, but here I'm being explicit. There's also value itself. Right, if decrement is low, we just want to recycle value itself through the flip-flop. So that gets that mux. Before we do the control lines for the mux, we also need a block of logic that produces a 0 flag. Well, that's fairly easy. We just take value into a block of logic that compares it with 0. And if the comparison is true, the 0 flag will go high. Finally, I need to determine the select lines for this mux. Some of them come from the input specifications. When latch is high, I want to latch in, so that has to be a select line. When dec is high, I want to decrement, so that must be a select line. And I want to stop when I hit 0. So the 0 flag itself is also a select line for this mux. Now you're saying, wait. You've got a 3 input mux with 3 select lines? And this is where synthesis does help you. I don't need to worry about that. I can write that mux like that in the code as an if-else statement, and let synthesis work out what it will actually be. Whether it actually will be an 8 input mux with 3 control lines to it, or some set of gates that lead to a smaller mux. I don't know, and it doesn't matter. Synthesis will work out what's reasonably optimum for this design. I don't need to get in that level of detail. So now that we've sketched out the design, what we do is translate it to Verilog. You've already seen the 3 constructs for synthesizable RTL. Think about it, go back to that if you like. What are those constructs would we use here? You might recall we said that anything coming out of a register has to be assigned in an always at POS clock statement. And we can put together that with a little bit of combinational logic, particularly that of a mux and its feeders in the same procedural block. So all of this that I'm circling now becomes one procedural block. I'll need a separate procedural block, a combinational logic one, or an assign statement to produce a 0 flag. So let's do that and look at the resulting code, and for the first time see a complete module that's a non-trivial example. So what I have here are 2 blocks of code. Note the ordering of these 2 blocks of code doesn't matter because we're modeling parallel hardware, and so Verilog lets you change the ordering of the code because there's no sequentiality implied by the ordering of these different blocks of code. The first block of code is triggered by always at POS clock. Obviously that's going to produce my register together with its input mux. Input mux, you think either case statement or if-else statement. This is a simple example, so if-else. Latch has priority, so if latch is high, value becomes equal to in. Else, if dec is high and we have not reached 0, value is equal to value minus 1. Notice I don't need an additional else for this wire here. Why is that? Why don't I need another else value equals value for that wire there? I can leave it as implicit, is the answer. What happens to the value of value if neither of the if statements are executed? That is, latch is low and either dec or low is low or 0 is high. What happens to value? It just stays the same. Right? Since it doesn't change, the behavior of the code is such that it has to stay the same. That is, we're implying there's a memory in this code. Well, that memory is intentional. We're intentionally building a register. So we don't need the else statement here to capture that final loopback. It's implicit in that value doesn't change if neither the ifs trigger the execution of a change in value. The second block of code here is a one-line continuous assignment statement. That is, we're comparing value against 0. Remember, double equals means is it equal to. This is producing a 1-bit true-false result that gets assigned to 0, which is a 1-bit piece of data. Notice, though this is not going to build a comparator, it'll actually go down to the optimal result, which is measuring NOR gates, that we don't need to think through what might be the logic structure. we can just describe the behavior of this in terms of it being a comparator and let synthesis work out what the optimal representation, what the optimal version of that logic is. Okay, now that we've seen the guts of the code, and you always approach this by writing the core of the code first, we need to fill out local variables and the ports. So let's go up to the local variables here. You can see there are two local variables. We need one local variable, either explicitly or implicitly, and I encourage you to make it explicit. The fact that 0 is an output means we didn't actually have to declare it here. But I encourage you to explicitly declare all your local variables. We need two of them, value and 0. Value is 4 bits wide, with the most significant bit on the left. I've specified it very explicitly, it's a big endian variable, and it's of type reg. Unfortunately, type reg does not always mean it's a register, though it happens to be in this case. Type reg just means it's assigned within a procedural block. All variables assigned within a procedural block take on type reg. And again, in this case, it's 4 bits wide. You'll notice that 0 is of type wire. The reason for this is that the rule in Verilog is that all variables assigned in a continuous assignment statement have to be of type wire or type trie. We'll come back to trie later. It's a fairly rare example. So most of the time, when you assign a variable in a continuous assignment statement, that like 0 is here, it will be of type wire. And all of the time, if you assign a variable after an always at statement of whatever type, it will be of type reg, whether it's a register or not. Finally, we have our inputs and outputs here. These essentially just come from the design. Notice that the input in is specified as being 4 bits wide, bit 3 down to bit 0, bit 3 being the most significant bit on the left. In the next set of notes, the verilog2 module will talk about other ways to approach this, how to specify little endian logic, little endian variables. But I encourage you to just stick to big endian. If you mix little endian and big endian, it can get confusing really fast. So that's what this design looks in RTL. Just a few notes on this before looking at it from some different angles. Again, multi-bit variables are specified using the structure shown on the top here. Here we have a 4-bit wide signal. The fact that the big number 3 is on the left means this is big endian. That is, the array that value is has value 3 on the left and value 0 on the right. And by the way, the basic data structures in Verilog are fairly straightforward. Everything is a bit or an array of bits, either of type reg, type wire, or trie. That's it. There's not much complexity beyond that. In addition, we saw a couple of constant numbers, 1 and 0. And here I'm going to introduce you to the specific way in Verilog that you can specify constant numbers. By the way, it would have been fine just to say 0 or 1 without this n-b in front of it. However, I encourage you to use this n-b because it's specifying the width of the number, and that can be useful in certain circumstances. So the way that constant values are specified in Verilog is, in general, we have this n-b value approach, where the first number is the size, and that's always in the number of bits. The next letter after the dash is the base, B for binary, and we'll come back to this in the next set of notes, but D for decimal, H for hexadecimal. The last thing is the value, which is in the base. So here the base is binary, value can either just be 0 or 1, or a string of zeros and ones. If we had dash H for hex, it could be a string of hex numbers. Don't worry about this too much. Just stick to the example on the page here. We're going to go through this in full detail in the Verilog 2 notes. And again, the concept in a procedural block is that when variables in the sensitivity list change value as indicated, in this case positive edge on the clock and only a positive edge, then the statements between a begin and an end execute in sequence, that is procedurally. This is much like how C is a procedural language. You actually only need the begin and the end if there's more than one statement in the block. So in the example I have here, there's actually only one statement, an if-else if, and I actually don't need the begin and the end. I'm just using this to illustrate the use of begin and end. However, there's no harm in putting begin and end in here. Continue on with some questions here, but before I do that, I remind you the continuous assignment just implements logic directly, and basically whenever the right-hand side changes, it gets reevaluated. But just to remind you through Q&A, when is the procedural block following the always at pos edge clock statement executed? Whenever there's a positive edge on the clock. When is 0 evaluated? Continuous assignment, whenever any variable on the right-hand side changes. How were comments done on the previous page? Hash hash, or put them between hash star to star hash. What does 1-B1 mean? A 1-bit constant with a value 1. And what does reg 3:0 value declare as a local variable? It's a 4-bit value, 4-bit variable, most significant bit on the left, and because it's type reg, it can only be assigned in procedural blocks. Let's turn this around and look at how behavior implies function. And here what I've done is color-coded the code correspondence to the logic. Again, if you look at the code, you can see this is the logic that would derive from it. Always at pos edge clock means a flip-flop. If else means a mux. The values in the parentheses are the control signals for the muxes. The values on the right are the values, are the inputs to the mux, in and value -1. For the combinational logic, what we're doing is comparing value to 0. That gives a true-false result that then becomes the flag 0. That brings us to the end of this submodule. Just to emphasize some major points here. Always design before coding. Sketch out the design at least to the register level before your fingers touch a keyboard. And then I suggest you even go further, get some idea of the combinational logic, and even simulate it in a simple timing diagram to get a feeling for yourself if you're on the right track. After doing design, then you start coding, and it's really just a translation exercise. Registers and input muxes become always at pos edge clock with if else or case statements inside them. Combinational logic becomes assign or always at star procedural blocks. What I'd like you to do now is proceed to the quiz for this submodule before going on to the next submodule. Thank you very much.